Yeah, I was a little bit sort of worried about talking about in a meeting on computational neuroscience because the last 2 years I haven't been really working in that. So what I'm going to do is start with something I did, which really was thinking of a problem in computational neuroscience, and show you where it's led me to work in more recent times. So this is not only network reconstruction, which is the problem we were looking at when I first started working on this, but also generative models. And in both cases, the subject is Meanfield methods. So just to get the terminology straight, for network reconstruction, what we mean is we have some system and we're trying to find the parameters of that system, like say, synaptic strengths, if it's a neural network, from dynamical data, like spike trains. For a generative model, you might have the same model, but you're using it for something else, right? You're given a system that generates some patterns, and you want to make your own system that generates patterns that are statistically indistinguishable from them. Okay, so that's a generative model. And as I implied a minute ago, these are not the same thing, but you can use the same methods for both of them. Oops. Okay, so here's a quick outline. The first bit is just going to review the fundamentals of statistical mechanics. Now, I put this in when I was preparing this because I didn't know how many people would have physics backgrounds and especially statistical physics backgrounds. So I'm going to start from the first chapter of Genesis here. And so normally statistical mechanics, if you don't specify it further, you're thinking of equilibrium things like the Boltzmann distribution, and I'll talk about partition functions, Icing models, and mean field theory. But what we really want to talk about is a dynamic thing, a stochastic process, and I'll show how you formulate that as a statistical mechanical problem. And then I'll apply that to making generative models for a peculiar and sort of interesting non-equilibrium 2D Icing model. And finally, trying to teach a recurrent network to compose music, which is the thing we're working on now. Oops. Okay. So first of all, statistical mechanics in a nutshell. So suppose we have some set of random variables, S1, S2, etc., n of them. And when I mean the whole set of them, I'll indicate it as a vector S. And there's some function we call the energy, which is a function of those variables. Okay. And the basic place you start with in statistical mechanics, usually, although you can get even more basic level, but I won't do that here, is the Boltzmann distribution, which says that the distribution of these variables is an exponential distribution of this energy. Okay, so it's e to the minus beta times E of S divided by Z of beta, which is just what you need to normalize things. And if you're not familiar with stat mech, then I have to tell you that you've heard of temperature, and beta is just 1 over the temperature. It's just more convenient for writing equations to write them in terms of beta rather than T. Okay, so actually it turns out the real interesting quantity you have to know is this thing in the denominator, which you might think, oh, I just need that for normalization. But it turns out you can get everything from the partition function, that denominator there. So here's a sort of trivial example. It's which is a completely general one. Suppose you want to know the average value of this energy. Well, that would be the sum over all the S's, multidimensional sum, over the energy for that configuration times the probability of that configuration, right? So you just put that, multiply E of S by the P of S up in the second line there, sum over S, and you get that expression. And then you realize you could have gotten that if you knew Z of beta, but just by differentiating with respect to beta and then dividing by Z again. And that's the derivative of the log of Z. Sorry, I say Z half the time and Z half the time. You just have to live with that. Hope it's not too confusing. Okay, so when you can put other parameters in the Hamiltonian and take derivatives with respect to them to get almost anything you want. So that's the whole story of statistical mechanics. This reminds me of an old story about Hillel, the Jewish scholar of 1st century BCE. Someone asked him, as you tell the story, often he was told that, can he tell the whole, recite the whole Torah standing on one leg? And he stood on one leg. He said, well, just don't do anything to anybody else that you wouldn't want done to you. That's the whole story, and the rest is commentary. So here, the rest is commentary. But he also told the student, now go study it. So here too, we have to go beyond that basic statement of it's the partition function and start to study it. So let's do that. We start by studying something simple. Simplest kind of variables are ones that can only take, say, 2 values, and we'll take them to be plus or minus 1. And if we were thinking about little magnetic moments in a material, then the energy is minus h times that plus or minus 1 if it's in a magnetic field H. So this is the sort of background for how this kind of model was developed. So that means that S equals plus 1 has a lower energy than S equals minus 1, and therefore it has a higher probability because the energy is E to the minus beta times E. Okay, I have to make a little digression here. Some people in machine learning define E with the opposite sign, but I'm stuck with the way I already learned it. If you learned it from machine learning people with the other sign, I'm sorry, I'll just try to flip it as I go along. So then P of S, the probability that S is some value is E to the beta times HS divided by the normalizing thing, which is the sum, that factor if S is 1 plus what it is if S is minus 1. So it's E to the beta HS over twice the hyperbolic cosine. If you remember the definition of the hyperbolic cosine. So that thing in the denominator, that's the partition function. And we can get, for example, the average S by differentiating log Z with respect to beta H. Okay, and that, because that's 1 over Z times the derivative. The derivative of the hyperbolic cosine is the hyperbolic sine, and the ratio is the hyperbolic tangent. Now, from now on, I'm going to take beta equal to 1 because it always occurs multiplied by these other parameters. So you could say really beta means beta H. H means beta H. Okay, now let's go beyond a single spin and look at the simplest model that you could look at. It's the Icing, well, think of it as a ferromagnet for now. But in this case, the energy, well, the second term there is for each spin, it's just the same thing describing the effect of a field on it. We'll let those fields be different in principle. And then the first term, the sum of Jij, Si, Sj, the meaning of that is that the parameter Jij, it tells you how strongly Sj influences Si, and in this case, also vice versa. So if it's positive, then you'll see that if the J's are positive, and then say the Sj is also positive, then the field is positive, and that wants to make Si, favors Si being the same direction as Sj. So mathematically, the Jij times Sj, that part of this for a fixed I, that acts like a field on spin I. So the probability of Si taking on a particular value, given all the others, that should say e to the Hi Si. Okay, that's the first misprint I've discovered here. Okay, so it's just like we had when we had an external field, but you use this internal field instead, which also includes the external field if it's there. So this really is the probability that Si is equal to +1. But in the general case, you put the multiply the Hi by Si in the numerator. Okay, so in general, that's an intractable problem. We need some approximations, although there are cases where you can solve for the partition function exactly, most famously by the most famous Norwegian in history, Lars Ansager. But I'm not going to talk about that. I'm going to talk about the more normal situation where we need approximations. And the basic approximation, which is called mean field theory, is you assume that these S's are independent random variables. Okay, and furthermore, you posit that each one of them has some average value. Okay, we won't say what those are. We're going to investigate all possibilities, but we're going to assume that S sub I has an average value mu sub I. And that means the probabilities of being plus or minus 1 are a half of 1 plus or minus mu sub I. So they sum up to 1. And then when we want to evaluate the energy, at least the average energy, we can replace the sigmas in the energy by the mu's because they're independent by virtue of the hypothesis of the approximation. So we just write the energy replacing the sigmas by the mu's. And that's going to be true for any set of mu's. But which mu's should we choose? Well, to evaluate the partition function, we needed to sum over all the sigmas, all the S's, plus or minus 1, sum e to the minus the energy. So here in this expression for the partition function is the e to the minus energy. And I have to now integrate over all these mu's. But I don't want to integrate over them with equal probability because consider the case where almost all the mu's are very close to 1. Then there's only a few such configurations. So that thing should be weighted very weakly. Whereas if the mu's are all about a half or something, then there are roughly 2 to the n configurations that have that kind of mu. So you need a weighting factor, and the weighting factor you use is e to the entropy. Boltzmann's basic idea in statistical mechanics was that the entropy is the log of the number of available states. So e to the entropy is the number of states. So in this case, we know what this entropy is for any choice of mu's that we make. Because first of all, they're independent, so you can get it by summing over the individual units separately. And for each one, you get minus p log p, summed over the two possibilities, right? So it's 1 plus mu over 2 log 1 plus mu over 2, plus the same thing with the minus sign. Okay, that's the first thing you'll ever learn in information theory. Okay, so we've got to do that big integral. And I'm not really justifying this, but in a large system and under certain approximation, under certain conditions, which are basically having lots of things connected to each other, this integral is going to be dominated by its value near its maximum value, near the maximum value of the exponent equivalently. So we want the maximum. So if I go back to this, maximum is S of mu minus E of mu. So we want the maximum of S minus E, or the minimum of what we call the free energy, E minus S. So how do we find that? Well, we solve df d mu I, that's n different equations in general. We solve them for the mu's. Okay, so if the mu zeros are the solutions of those equations, then the log of z is just minus f of mu zero. Now there is I'm not able to see all my slide. Can I get rid of this? Yeah, okay. There's pictures of everybody else on the side of the screen there. Okay, now I can see the whole thing. Okay, so how do we do mean field theory for that Icing model? Well, we need to take those derivatives. So the derivative of with respect to mu sub I is just this field, sum of jij mu j plus an external field if you have one. And in an exercise of high school algebra, the derivative with respect to mu, which of the entropy, turns out to be 1/2 the log of 1 plus mu over 1 minus mu. And yeah, the first time I saw this, I thought I was seemed like magic. It turns out that's the same as the inverse hyperbolic tangent. Okay, so these two derivatives are supposed to be equal, and you take the hyperbolic tangent of both sides, and you get that the mu zero is the hyperbolic tangent of that field from the others. Okay, so that's the basic equation of mean field theory for a ferromagnet. And in fact, if I have a particular kind of ferromagnet, so a ferromagnet has been all the JIJs are zero, or at least most of them, then this is exact if the JIJs are small and the system is big. So they have to be of order 1/n as n goes to infinity. That's called the mean field limit. So, okay, so the simplest case is where all the JIJs are equal and all the H's are constant. And so all those equations are the same for every site. And you just get this familiar thing. And I know you've seen this in other lectures here at this school, because it comes into the Hopfield model, which is basically built on an analogy with this. Okay, so now I have to talk about spin glasses. So I have 1 or 2 slides about that. So in a spin glass, all these coupling constants are the J's, they're quenched random variables, right? So you can imagine making many samples. Each one, it's a different set of J's. Typically, we take them to be from a unit Gaussian, so just as likely to be positive or negative, although you could bias them a little. And each one of these samples has its own thermodynamics. Each one you could try and do mean field theory, solve those n equations. But on the average for certain quantities, like the energy, so on, it doesn't matter which sample you're looking at. But still, the fact that these things are quenched random variables, and you can see it most clearly when they have zero average, then this mean field theory isn't correct. Even if the variance of the J's goes small when the system gets large. Okay, so it was recognized early in the history of spin glass theory that we needed a better mean field theory for even to do mean field theory correctly for spin glasses, and by extension for other highly inhomogeneous systems. So in 1977, David Thowles, Phil Anderson, and Richard Palmer showed how to do a correct mean field theory for spin glasses. And it was a frustrating paper because they didn't really say how they got it. But the answer is quite simple, right? It says you got to change the energy term in the free energy, right? So the first and last terms here are just the ones you'd have in naive mean field theory. But when things are fluctuating, the next thing you get is something involving where there was J before, you get the Jij squared, right? And you obviously need this because if the average J is zero, then the first term isn't there at all. So you have to go on to the fluctuations. You get sort of the variance of one of the spins interacting with the variance of the other through the square of the J. And you get a half because whenever you expand to second order, you get a half. And this variance of the given spin is it minus its average squared and averaged. But since the square of the spin is always one, this is just one minus mu squared. So you just change the energy term. The entropy term, you don't have to change at all. You have to solve df d mu equals 0, all n equations of it for a particular sample. And in the model they were looking at, where the variance is like 1 over n and n goes to infinity, this is exact. You don't have to go any farther. But in general, you could look at higher order terms in this and ask Yasser how to do that, because he's an expert on that. Okay, so much for equilibrium statistical mechanics, but we want to do something with dynamics in it, because we're interested in making dynamical generative models. So again, we're going to start with a single spin in a field, and it's going to evolve in time. And the rule I'm going to give is that at each time step, so this is digital time, at each time step, it just takes its next value with the Boltzmann probability that it would have for the current external field. So you have a sequence of H's which depend on time, and that produces, by this rule, a series of random, because it's probability, a random series of S's. Okay, and we could write the probability for the whole history. It's just the product over all the time steps of this Boltzmann-like factor for the single time step. Now let's proceed like we did for the equilibrium case. I'll make a network of spins, and I'll just say at each time t, each spin fields the field of other spins, just like we talked about in the Icing model. Sum of jij times sj of t. And we get the probability of the history of just multiplying these factors with this h instead of the external h. And so there it is written out explicitly, reminding what h is. I could stick in an external field, a little h here as well, but I'm trying to make the equations as simple as possible. And that doesn't add anything conceptual to put those back in. That's a homework problem. Okay, so suppose we want to do, well, what you call the inverse problem or the network inference problem. So it's not like we want to know properties of the time series that comes out of this. That would be the normal thing you would do in statistical mechanics. But suppose we've measured all those S's, measured the whole time series, or at least examples of it. And what we want to find is what J's most likely caused that. Okay, that is, we want those that maximize the probability of getting the observed S's maximize over the whole possible values of J. Okay, and as always in statistics, we talk about the log of the probability instead. This is called maximum likelihood. And so what we want to maximize is the log of P. So the log of that, let's go back to, so then the log of P is now a sum of the logs of these things. And the log of e to the s times h is s times h itself. Then you've got to subtract the log of twice the cosh. And so what we get is this log of P is a simple looking term connecting Si of t with J of t with Si of t plus 1 through the coupling Jij, minus this funny looking log twice the cosh of the h. This is log P, which we want to maximize. You remember we talked about the energy in statistical mechanics was minus the log of P. So we want minimizing the energy is the same as log maximizing the log likelihood. Okay, and so, well, still talking about maximizing the log here, we want to make changes proportional to the derivative, make changes in the J's proportional to the derivative of the log likelihood with respect to the J's. And differentiating that, okay, well, from this term, you just get Si of t plus 1 times Sj. Differentiating log cosh, as we have said, gives you the hyperbolic tangent of h. And you got to differentiate h with respect to s and with respect to j, and that gives you the s. So it's this common thing you find all over learning theory of the error on the output, what it turned out to be minus what you expected it to be on the average, multiplied by the input. Okay, and that's very easy to implement. The problem gets interesting when we don't have all the spins observed. Right? Suppose we have a whole bunch of spins that we have measured in the way I just described, but now I have a bunch of spins, which I'll call sigmas, and we'll just call them the hidden spins or unobserved ones. Now I have to worry about 4 different matrices, not just the J's. We have the J's, which are the visible to visible connections. There's also some connections from the hidden to the visible, which I call K. There's ones which go in the other direction, from the visible to the hidden, which I call L, and the hidden to hidden ones I call M. So now the visible units feel an H, which is like the one from the other visible units, plus the sum of KIB times sigma B at each time step. And similarly, the hidden units feel something proportional to the visible ones plus sum of MAB sigma B. So these are interactions among the hidden ones. And the log likelihood of the whole thing, forgetting about which ones are visible and which ones are hidden, which ones are measured, you get this term we had before, and the same term, same kind of term, sigma times B minus log cosh 2B, where B is the field on the hidden parts. Okay. Now, we want to do our inference problem again, but we've only measured the S's, not the sigmas. So they have the distribution, you just marginalize out the sigmas, you sum over those, some of this joint probability, which is what's up here, over the values of the sigmas. Okay, or another way you can say this is the conditional probability of the sigmas given the observations we've made is from Bayes' rule just the joint probability divided by the probability of the S's. And the probability of the S's is just what we have here. So this equation has a form of a Boltzmann distribution if you identify minus the log of the joint probability as the energy. So this big long line up here is the energy, this problem. And the denominator here is just what you needed to get the partition, is just what you get by integrating out or summing out the observed values proportional to their probabilities, right? Okay. So this is a statistical mechanical problem in the sigmas. The S's in this case we're thinking of as we know them, they're observed. And we're going to do our learning problem to find the couplings with on the basis, all conditional on that observation. Now, I just want you to notice in this problem, the sigmas, this is unlike the equilibrium statistical mechanical case. The sigmas have indices, both or indices or arguments, which both label which unit it is and what time it is. So time enters, this digital time here, enters here on the same footing as the way you identify which unit. Right, so if you were talking about a lattice here, you have a space-time lattice that you're talking about. But the equations all look the same. So I know, especially if you're seeing this the first time, these are beginning to look like long equations. But I'm trying to do this in such a way that each one is sort of just an elaboration of a pattern you've seen on a previous transparency, on a previous slide. So, for example, the first term here, we understood what that was, thinking even of a single spin. And now we've just added a term like it for the hidden ones. And of course, this looks trivial, but the connection is that the sigmas occur both in the H's and the B's. So It's a non-trivial problem. Okay, so this is just what I just said. We have a statistical mechanical problem in the signals. Now, we can do naive mean field theory, just like we did in the ferromagnet. Just assuming the sigmas are independent, replace each one by its mean. Okay, the only thing that's different is the sigmas and the mu's are labeled by time as well as which unit they are. And minimize the free energy. Okay. And it's just this thing, we've got to do two kinds of problems here. One is we've got to do the mean field problem for this energy, right? So that means minimizing this with respect to mu, or the same equations, df d mu equals 0 for a given j. And we also, for those mu's, once we've solved that statistical mechanical problem, we have to minimize the energy given those mu's. So we take turns doing one and then the other. There's a name for this in mathematical statistics, but I can't remember what it is. Okay, so if you know the mu's, then learning the couplings is simple. It's just like what we did when they were all visible, right? Because you do it assuming you've got the right mu's, right? So, for example, the K's, there's the output unit is the visible one, so this is the error on the visible one. But since the input unit is a hidden unit, it's the mu that occurs here instead of the S. And the L is the other way around. It's the error on the hidden unit. And for the M, it's both the error and the input are hidden. Okay, so the part which I skipped, maybe I should have done it first, is you want to set df d mu equal to 0, right? For each mu sub a of t, you want to differentiate that naive free energy with respect to it and set it equal to 0. Okay. So I'm going to go back a few slides, just show you where this comes from. So part of it is differentiating the energy. So where does mu occur in the energy? Well, one place it occurs is in the B here, right? Because the B includes the sigma, but we're replacing the sigmas by mu's. So we're going to get a term from differentiating this. Sorry. It's both places, okay? But the one I wanted to talk about first is that here's the sigma of t plus 1, and that's going to be mu of t plus 1. So the mu's are right there, and they're multiplied by a b. So that gives us our first term in df d mu. The others all come from this dependence of b on the mu's when we make that replacement. So we'd have to take sigma mu of t plus 1 times differentiating b with respect to mu, and that is going to give you, m and similarly, differentiating the log cosh, that gives you a tangent. Again, you have to take a differentiate the B with respect to mu. And so in both cases, you get dB d mu. And you wind up with this error thing on the input at the next time step times the n. Okay, and the same thing happens in the other term. You get the error on the output times the k. Okay, so this is the term you would have just looking at the feed forward thing. And this is where the sort of back propagation in time comes from. Right? Each one sort of feels the error sent back through the matrix from the following step in time. And now when you differentiate the entropy, you get that inverse tangent. So you get this equation. So you should solve this equation for mu. So ideally, each step you get a new mu from solving this. We found that sort of unstable. So we fixed that by the simple kludge of only going partway toward the new mu. I won't go into any more details about that. So now we have both parts of this learning that we do. But there are problems with this. So let's look at those log cost terms a little more carefully. So,
hey, John.
Yes.
Just on this slide, what is function f? The first line.
Free energy.
Oh, the free energy. Okay, so this is the same one that we saw on the previous slide.
Yeah, it's this energy minus the entropy.
Okay, thank you.
Okay. It's not the one from the ferromagnet. Okay. Any other questions while I'm stopped here? Okay, so I'm just going to try and finish this section before we take the break. So I'm going to go back to look at the terms in the energy. So, there's this unfamiliar looking non-polynomial term in H. And let's imagine expanding it in K. And we'll expand it around, say, just the visible input to the visible units. We're looking at what happens to the visible units here. So it's the log cosh of this plus the derivative of that times the part proportional to k, and the first order term, and then second order term is 1 minus tanh squared. And then you get the sum of k times sigma squared, kia, kib, sigma a, sigma b. And if you just replace the sigmas by mu's, you'd be making an error here, okay? Because when a is equal to b, then you should be getting 1. But if you just blindly replace sigma by mu, you'd get sigma a squared, right? So we can correct for all those errors by expanding around the case, the H0, which the one you would get if you replaced the sigmas by mu's everywhere. And then there's no linear term. And the first thing you get is a quadratic term. And it's got 1 minus tanh squared, which is the second derivative. And just the correction that you have to make. You should be getting 1, and you get what you were getting is mu squared. So you get a term like this. And you can take this to higher order, but I won't talk about that here. So to this order, we can fix the problem by sticking this term in the energy. This is just the extra term that we just added. Okay, and we can do the same thing for the hidden units. Now, if you were listening when I was talking about tap, these things look sort of tap-like, right? This is a sort of fluctuation-looking term. This is 1 minus mu squared. It's another one. Same here. And what comes in the middle is a coupling squared. So it's looking sort of like tap. But if you look carefully, the sign is the opposite. So it isn't really a tap term. It's just the way you compensate for this bad counting that you would have done if you blindly replaced the sigmas by mu's. Okay, so there's a second problem. Here's the energy function again. And if we look at this term, which is sigma A of t plus 1 times BA of t, well, BA of t is the sum of, on B, should be also a sum on B in the second equation here. Sigma A of t plus 1, MAB sigma B of t. This is a pair interaction just like in a ferromagnet. Right? It's just M's instead of J's, and it connects things at different times. But we're just regarding time as an index the same as the unit index or space index. So we know how to deal with that. Tap told us you stick in 1 minus mu squared at t plus 1, MAB squared times 1 minus mu A squared, and stick a minus a half in front of it. Okay. Actually, the MAB squared and the 1 minus mu A squared, that same thing was there in the second term that we added already. So you can combine those nicely so that the second term is mu squared of t plus 1 minus tanh squared of B, and then m squared times 1 minus mu squared. Okay. Now, this was derived by Ben and Yasser in a very different way, but I just wanted to present this derivation because I thought it at least helped me see where things came from. So you just add these terms to your energy and then follow the recipe. You alternately adjust the mu's and the coupling constants based on gradients of this augmented energy function, the one with these extra terms in this. And this is what I call tap learning. Okay, and now I think it's time for a 5 or 10 minute break. And when we come back, I'll show you how we tested this on some fun examples. Okay, so, we tried, and I think Ben and Yasser also tried using this pretty theory to try and do network inference. And I have to say the results were kind of limited. If you knew most of the network and there were only a few hidden units, you could get them. But in anything like a biologically realistic case, where you only could record from a few of them, you would need to record forever to learn enough to identify all the missing couplings. So, acting on the notion, we have this beautiful theory. If this is the answer, what is the question? We decided to ask another question. And that's what led us to think of using it as a generative model. So now if I can share the screen again. And I hope you can all see that. We're we wanted to try it using it as a dynamical generative model of a sort of fun non-equilibrium Icing model. So it's a 2D Icing system. Well, this isn't the version of it that was originally made, but it's close enough. Right? So this original version was by a guy named Tome, I'm not sure how to pronounce that. It's an Icing model with asymmetric bonds. So the spins feel only themselves and the neighbors to the east or north of them. So either above or to the right. The arrows in this graph are trying to show you. They also feel, as the circle indicates on each one, that they feel themselves. So the field on at a point, so here the ij represents, you need two numbers to say a point in the lattice. The field on the spin at point ij is, you get just from summing up its own value with the values of its north and east neighbors. Okay, so in the original version, it was, instead of sticking and summing these up and taking the Boltzmann factor, it was in a version where they simply took a majority vote of these things. So in the limit of strong coupling, it would be the same thing. Now this is too easy for our model to try to solve because we wouldn't even need hidden units to do it, because as you see, the couplings are just among these hidden units. So to challenge the network a little bit, we added a little nonlinearity. So we raised this h to a power gamma, and each time step, we took the new h and only took a contribution proportional to x of that, and 1 minus x is its previous value. So it sort of makes things sluggish. It gives it some memory. It's not an instantaneous in time thing. So what I'm going to show you is some simulations on a 10 by 10 grid when this exponent is 3 and the delay parameter, or whatever you call it, x is 0.3. And it's actually a northwest center model, not a northeast center model, the way we did it. I'm just going to try to show you now what it looks like. Okay, so
you see freeze?
it's on 50. Is this visible?
Yeah, we can see it. The audio is a little choppy at the moment, but you can see your screen.
But we don't need.
Okay, so it should be some sort of, this is what reminds me of a Danish weather map. So the
John, are you there? You lost the share screen, and I think you're muted now. Yeah, I think MATLAB might have been too heavy to have with Zoom.
I'm unmuted now, I think.
Yeah.
It says my internet connection is unstable. Let me just try it one more time. Oh no, that's, sorry, wrong
This is Python.
Here. Okay, can you see it?
It's coming.
While we were broken off, there time went on, and these islands are getting bigger because as it's kind of nucleating. But I've this to be near.
No, we haven't seen yet.
No, yeah,
It's what?
yeah. There we see it. Now we see it. Yeah.
Okay, I'm going to stop it now if I can. Okay, now I have to find the. Okay, so that's what it looks like in bigger scale. The actual simulations, just because we have small computers, are done in a 10 by 10 grid. And so this is just some learning curves. So the first one shows the negative log likelihood per spin and per time step. So I didn't write that part explicitly, but it's in bits. So random performance would be 1. Perfect performance would be 0. You can see you were a little over a half here. So it doesn't look like it's that good. The red line is the test set and the blue line is the training set. But if we look at the next graph, you see it isn't so bad in terms of scores. Even though the test NLL is going up, the scores are still pretty stable, though it's not quite so good for the test set. And in fact, if you test the model on itself, so at each time step, you make this random choice of the next things. And when you do that, you make another such generation of a possible at the same time, and you compare two, and you ask how often are those two the same? And the answer is 81% of the time. So actually, this has learned this fairly well. So because of the time, I'll go through this quickly. We did the same calculations for the naive mean field theory, ignoring the TAP terms. And the at first paradoxical thing is that you see that the scores are actually better than they were for TAP. So what's happening? Well, I cheated. When I tested the NMF, the naive mean field theory model, I used continuous valued hidden units. Whereas when I tested the TAP model, because it was supposed to be a theory of stochastic units, I used stochastic hidden units. So the continuous valued hidden units are more powerful for this size network anyway than a stochastic binary unit. In fact, you see it went up to a value above what you got from the NEC system predicting itself, which seemed kind of paradoxical. And I'm not sure I really understand that, but I think it may come from the fact that it can use, the network can get information from the whole grid, and that's more informative about the next step statistically than just knowing the neighborhood, which is what the NEC model itself was. If this is true, then if I take a big enough TAP network, it should also do better than the original model in this paradoxical way. Okay. So this made us think of naive mean field theory in its own right, even though it's deficient as a theory of stochastic systems, as a learning algorithm for recurrent networks. So it's a way of training a recurrent network with continuous valued units. without using backpropagation through time. And backpropagation through time is what makes doing recurrent networks kind of messy, because I will try to summarize this slide quickly because of the shortage of time. But you have to sum over all paths from all visible units in the future back to the unit you want to know the error on. And in the naive mean field theory way of doing it, that's all done implicitly when you write down the energy function. And then each mu is only connected with ones at neighboring steps in time. Okay, so we've applied this to a music problem. So Johann Sebastian Bach arranged 382 traditional German hymns as 4-part chorales. And here I'm taking these in a simplified version, quantized into quarter notes, or if you're English, crotchets. We got the data from Joshua Bengio. So the input in our network is a time series of 4-dimensional, well, when you're learning, is 54-dimensional vectors. You're thinking of a piano keyboard, but not all the keys are used. So it's only 54 instead of 88. I think in Bach's time, keyboards were smaller, or at least we just used all the notes that he used. And the way it's coded is that component of the vector is 1 for the key that's played and 0 or -1 for the ones that's not played. And we just trained some fully connected recurrent nets of the kind we've just been talking about on the first half of each of 64 chorales. Okay, and then so I'm going to give examples for chorale number 4 here. So you train the net you prime it on the first measure, so the first 4 notes. You force the network through getting the right answer on the first 4 notes of whatever your learned chorale you're trying to continue, and then let it continue to run, feeding its output back into the input. And usually, as you'll see in the cases, it was trained on the first half. And in this case, the first half was 8 measures, 32 notes. And usually it gets the part that it was trained on correctly, if it's been trained well enough. But then it's on its own and it starts to compose new stuff. And I, in this example, had it compose 12 more measures. So I'm going to give you some examples, and I hope that the sound works better than the vision. Several notes that, several networks that we used, differing in how many chorales we trained on, how many hidden units we had, and how many iterations it took. But all of these were trained to getting negative log likelihood per output unit per time step of 0.02 bits, right? 98% of the way, all the way down to 0. Okay. So for this, first I'm going to play you the chorale as Bach wrote it and as quantized by Bengio. Okay, that's probably pretty jarring if you are used to how beautiful those sound when they're actually done by a choir, but that's what I could do. So maybe because the time is short, I'll only play a few of these. So here's one. It had 64, trained on 64 chorales, had 256 hidden units. We trained it for 30,000 iterations. Okay, I'll move it forward. Well, all right, continue again. You see, it's continuing correctly from that little seed we gave it of the first measure. And okay, and this is as far as it's been trained. So now it's going to diverge from what Bach wrote, because it never heard what Bach wrote. Okay, so you can see that it sort of sounds like Bach, right? It doesn't know how to end. Did you hear that?
Yeah.
Okay. I'm only going to play one more. This is the one with 512 hidden units. It'll only play the part where it's continuing on its own. Okay, now I think I won't play any more because we're running out of time. But I'll just mention a few things we learned. One is that you have to overtrain, surprisingly, in order to get anything that sounds good. So the old prescription of have a test set and see if it can do the test set just doesn't work at all for this problem. But it's not really what we're trying to, what you want to do. If you have a student wanting to learn to play the piano, you have him or her learn the things right and then see how to generalize from that. So maybe the machine wants the same thing. I should say at the input, I not only used the last note and had that be the basis of what you predict the next one on, but the whole last two measures. Okay, and that helped a lot. Another thing that helped a lot was having the matrix, coupling the hidden units, be an orthogonal matrix. And it also, going with that, we, instead of using a hyperbolic tangent activation function, we used this thing we learned from Joshua of the modified, rectified linear unit. So it's one which makes a sort of more symmetric version of our ordinary rectified linear unit. We had the J's in the problem, the visible connections. It turns out, at least when we got done training, we could remove those and it didn't make any difference. In fact, training the hidden connections in this big orthogonal matrix, that only helped a little. So that's a little bit reminiscent of reservoir computing, where you just take a random matrix there. However, it was important to train the input to hidden connections, which you don't do in reservoir computing. We could get almost the same kind of results with reservoir computing, where you only train the hidden to visible units, the Ks. But it's much slower to train and requires many more hidden units, a factor of 16 in some examples. So there's some things we'd like to know. We're just sort of scratching the surface of this. One is that, as you might guess, learning gets harder and harder the bigger the training set is. So we're wondering, does depth help? Other architectures, we started to explore those. Another thing is, if you look at the errors that it makes, even when it's getting this really low negative log likelihood, it's getting more errors on the keys that you want to play than on the ones that you don't. So you can bias the training to, learn stronger on the notes you want to play. And it's some indication that may help. And one of the recordings I was going to show you was generated that way, but I don't have time for it. I said you had to overtrain, but in really small sets, we could really train to death down to 0.001 or something. And then when we tried doing this procedure on them, it would take the part that it was, get the part that it was trained on perfectly, and then just repeat it and repeat it. It didn't really compose anything new. So maybe you shouldn't go all the way down, but what's the optimal degree? We don't know. And one question in this, we're carving out a landscape in the space of sequences here. And we'd like to make the ones we want some kind of attractors. And we'd like this to be robust. So maybe tricks like dropout in training would do that. And we haven't planned to study that more, but just at the beginning of that. So that's the end of what I have to say. And I just want to give thanks to Joanna Tyrke in Stockholm, who was my collaborator on all this work. And finally, I wish I could be there in Eresfjord with you all in person.